The night Stephen Hawking discovered that black holes explode, he was getting into bed. Not sitting at a desk, not surrounded by chalkboards and colleagues. Getting into bed, slowly, carefully, the way he had to do everything by that point in his life, and somewhere between standing and lying down, in the dark, in January of 1974. The entire framework of how we understand the universe quietly cracked open inside his head. He couldn't write it down. He couldn't call anyone. He couldn't reach for a pencil. So he just lay there, holding in his mind a discovery so enormous it would take the rest of physics 50 years to figure out what to do with it. That is not a dramatization. That is what happened. And what he found that night didn't just change what we know about black holes. It broke something much deeper, something that the smartest people alive are still trying to fix. Before I tell you what he actually found, I need you to understand something about the man himself. Because the story of Stephen Hawking is one of the most genuinely strange stories in all of science, not because of what he survived, but because of what he built while surviving it. Most of what people think they know about Hawking is the surface version, the wheelchair, the voice, the brief history of time on everyone's shelf, read by almost no one past chapter 2. But underneath all of that is a sequence of ideas so radical, so counterintuitive, so mathematically violent, that even the physicists who disagreed with him couldn't stop talking about him. He was born in Oxford, England in 1942. 8 years after, by the way, Albert Einstein published his unified field theory. 300 years, almost to the day after Galileo died. Hawking liked to mention that coincidence. It was either a cosmic alignment or a man who really knew how to work a biography, possibly both. He was not a prodigy in the obvious sense. He was bright, famously untidy, the kind of student who never seemed to work very hard and still outpaced everyone around him. He got into Oxford at 17, coasted through on charm and raw pattern recognition, and arrived at Cambridge for graduate school in 1962 with the vague intention of studying cosmology, the science of the universe itself, how it began, how it works, how it will end. He was 21 years old, and the world was wide open. Then, within a year, he started dropping things. The diagnosis came in 1963, motor neuron disease, a condition that progressively destroys the nerve cells that control movement, leaving the mind entirely intact while slowly dismantling the body around it. The doctors told him he had 2 years to live. He was 21 years old. And here's the part that gets glossed over in most retellings. He nearly gave up. He spent months in a kind of numb paralysis, unable to see the point of finishing a PhD he might never use, doing work that might die with him before it mattered to anyone. That is not weakness. That is a completely rational response to being told your body's going to stop working while your brain keeps going. What pulled him out of it was, of all things, a man named Roger Penrose. Penrose was a mathematician at Birkbeck College in London, and he had just done something quietly extraordinary. He had taken Einstein's equations about gravity, the general theory of relativity, published in 1915, and he had pushed them further than Einstein himself was willing to go. Einstein's equations described how mass warps space and time. Penrose took that logic to its extreme and proved, mathematically, that if you compress enough mass into a small enough space, the equations stop working. Space and time collapse into a single point of infinite density, a singularity. In simple terms, he proved that black holes, if they existed, had to contain a point where all the known laws of physics break down completely. Not bend, not stretch, break. Physics itself stops being physics at the center of a black hole. This was either the most exciting result in theoretical physics in decades, or the most terrifying, depending on your disposition. Hawking heard Penrose give a talk about it, and something switched on. Not just academically, existentially. Because Hawking realized that what Penrose had done to the future proving that stars collapse into singularities could be run in reverse. You could apply the same mathematical logic to the past, and if you did, you got something even larger. You got a proof that the entire universe, the whole thing, all of it, began at a singularity. A single point of infinite density, what we now call the Big Bang, but with the mathematical teeth to back it up. Hawking threw himself into that problem. And I want you to sit with the image for a second of a man whose hands were already beginning to fail him, whose speech was already starting to slur, working with Penrose on theorems that required pages and pages of tensor calculus, and doing it not despite the disease, not ignoring it, working around it, through it, finding ways to hold the geometry of space-time inside his head because he couldn't always hold it on paper. His spatial intuition became extraordinary, not as compensation, as necessity. In 1970, Hawking and Penrose published what became known as the Penrose-Hawking Singularity Theorems. The proof that, under very general conditions, consistent with Einstein's relativity, singularities are inevitable. Not a mathematical curiosity, not a special case. The universe began in one. Massive enough stars end in one. This was a landmark result, the kind of result that gets you into textbooks. And Hawking was 28 years old. By this point, by the way, he was using a wheelchair full time. His speech was difficult for strangers to understand, though people close to him still could. He was married, had children, was supervising graduate students, was doing the full architecture of an academic life while navigating a body that was closing in on him one system at a time. And he was just getting started. Now, here is where things get genuinely strange, and I need you to stay with me. Because what I am about to describe is one of the most unexpected collisions in the history of science. It involves black holes, quantum mechanics, and a discovery that Hawking almost refused to believe himself. But first, I need to explain something about black holes that most people get slightly wrong, because the wrong version makes the discovery sound impossible, and the right version makes it sound inevitable. A black hole is not a hole. It is not empty space. It is the opposite of empty. It is a region where so much mass is compressed into so little volume that the escape velocity, the speed you would need to reach to get away from it, exceeds the speed of light. And since nothing travels faster than light, nothing escapes. Not matter, not radiation, not information. The boundary where this happens is called the event horizon. And for most of physics history, the event horizon was considered a one-way door. Things go in, nothing comes out, end of conversation. Black holes were, by definition, perfectly black. They emitted nothing. They absorbed everything. They were the universe's most efficient vacuum cleaners, and they were eternal. That was the consensus in 1973. 1 year later, Hawking would prove it was wrong. Completely, irreversibly, magnificently wrong. Here is what he found, and I want to explain this carefully, because it is genuinely one of the most beautiful ideas in all of physics. Quantum mechanics, the physics of the very small, the physics of particles and energy at the subatomic level, tells us something deeply weird about empty space. Empty space is not actually empty. It is constantly churning with what physicists call virtual particles. Pairs of particles, a particle and its antiparticle, spontaneously popping into existence together and then annihilating each other almost instantly. They borrow energy from the vacuum, exist for a tiny fraction of a second, and then pay it back. This happens everywhere in the universe, all the time, constantly. Space is full of this invisible froth of borrowed existence. Your room is full of it right now. Slightly unsettling, but there it is. Now put that idea right next to a black hole's event horizon. If a pair of virtual particles pops into existence right at the edge of the event horizon, one particle on the outside, one particle just inside, something extraordinary can happen. The particle inside gets pulled into the black hole, the particle outside can escape into the universe. But they were supposed to annihilate each other. The energy was supposed to be paid back. So where does the energy come from? It comes from the black hole itself. The black hole loses a tiny, infinitesimal amount of mass and energy to allow the outside particle to escape. And that escaped particle is what Hawking radiation is. Black holes don't just absorb, they emit. Slowly, over unimaginable timescales, they bleed energy. And if they bleed enough energy, eventually they evaporate, they shrink. And at the very end, when they are small enough and hot enough, they do not go quietly. They explode. The most destructive objects in the universe are slowly dying, and eventually they go out with a bang. Yep, you heard that right. Hawking published this in 1974, and the initial reaction from the physics community was not celebration. It was something closer to polite hostility. The leading experts in black hole physics looked at his calculations and told him he had made an error. Peter Bergman, one of Einstein's own collaborators, was in the room when Hawking first presented this publicly, and the chairman of the session essentially tried to shut him down. The result was too strange. It contradicted everything. Black holes were supposed to be black. They had always been black. The math said they were black. Hawking's math said otherwise. And within months, after other physicists checked his work, after Jacob Bekenstein's related calculations about black hole entropy were brought into the picture, the field did what science is actually supposed to do. It changed its mind. Hawking radiation became one of the most celebrated theoretical results in physics in the second half of the 20th century. A result so important that most physicists consider it proof that Hawking deserved a Nobel Prize, except for one inconvenient problem. Hawking radiation has never been directly observed. It is so faint for any black hole massive enough for us to detect that our best instruments cannot see it. The Nobel Committee does not award prizes for theoretical results that have not been confirmed experimentally. And so the man who arguably made the most important theoretical contribution to physics since Einstein never got the prize. The universe has a genuinely cruel sense of humor. But here is the thing. Here is the piece that does not get told in the documentaries. The thing that most people who read A Brief History of Time do not realize is lurking in Hawking's discovery. Because Hawking radiation is not just a beautiful curiosity about black holes evaporating. It contains a bomb, a philosophical bomb, so powerful it is still detonating today, 50 years later, inside the foundations of physics itself. Think about what happens when a black hole evaporates completely. Everything that ever fell into it, every star, every planet, every atom, every particle, every piece of information about the state of every object that crossed that event horizon was inside that black hole. And now the black hole is gone, evaporated. The radiation it emitted on the way out, according to Hawking's original calculation, is thermal radiation, random. It carries no information about what went in. And this is where physics has a full-scale breakdown, because there is a principle in quantum mechanics that is not optional. It is not a guideline. It is one of the absolute bedrock rules of how the universe works. It is called unitarity. And in simple terms, it means this: information is never truly destroyed. The universe always, in principle, remembers everything. You can burn a book, and the information in that book still exists in the precise positions and energies of every particle of smoke and ash. In theory, with infinite precision, you could reverse the process and get the book back. The universe keeps records. Except, if Hawking was right, black holes destroy those records. Everything that falls in is gone. Not scattered, not encrypted. Gone. The information does not come out in the radiation. It does not come out at all. It is destroyed. This is called the black hole information paradox. And it is not a small problem. It is a conflict between general relativity, the best theory we have of gravity and large-scale structure, and quantum mechanics, the best theory we have of particles and small-scale structure. Both theories are extraordinarily well tested. Both are extraordinarily successful. And they are telling us opposite things about what happens to information in a black hole. At least one of them has to be wrong, or at least incomplete, and we do not know which one. Hawking spent decades arguing that information really is destroyed, that this was simply what happens. That quantum mechanics, as beautiful as it is, had to make room for the possibility that some information is lost forever inside black holes. The rest of the physics community spent decades arguing back. Some of the most brilliant minds in theoretical physics, Leonard Susskind, Gerard Hooft, Juan Maldacena, argued that information cannot be destroyed, that Hawking had to be missing something, that the radiation leaving a black hole must secretly encode the information about what went in, even if we cannot currently see how. This is where my subplot comes in, and I promised you I would come back to it. In 1975, Hawking made a bet with a physicist named Kip Thorne and another named John Preskill. Hawking and Thorne bet that information is destroyed in black holes. Preskill bet that it is not. The prize was an encyclopedia of the winner's choice, to symbolize the preservation or destruction of information. Yep, that was the actual bet. Kip Thorne, for those who do not know him, is one of the greatest living physicists, the man whose theoretical work on gravitational waves helped make the LIGO detector possible, the man who would win the Nobel Prize in 2017 for confirming a prediction Einstein had made a century earlier. He is not a person who makes casual bets. He was serious, and for 30 years, he stood by Hawking's side. Then, in 2004, Stephen Hawking stood up at a conference in Dublin and announced that he had changed his mind. He said he had found a new way of calculating what happens to information inside a black hole using a sum over histories approach in quantum gravity, and that the information does come out, that it leaks through subtle correlations in the radiation, encoded in a way that is almost impossibly complex but not fundamentally lost. He conceded the bet, he ordered an encyclopedia, he sent it to Preskill. Thorne refused to concede. He said he was not convinced by Hawking's argument, which tells you something about the difficulty of the problem. The man who proposed the information paradox changed his mind, and his co-bettor still was not satisfied. The information paradox is still not fully resolved. In 2012, a paper by Ahmed Almhiri, Donald Merolf, Joseph Polchinski, and James Sully, the four authors whose names gave us the acronym AMPS, proposed what they called the firewall paradox. They argued that if information does come out of a black hole, the event horizon cannot be the smooth, quiet boundary everyone assumed. It would have to be a wall of high-energy radiation. Anything crossing the event horizon would be instantly incinerated, which contradicts general relativity, which says the event horizon should be locally undetectable. You would cross it without knowing, which meant either general relativity is wrong at the horizon, or quantum mechanics is wrong about unitarity, or there's a third option nobody had thought of yet. The firewall paradox broke physics again, with fresher, sharper pieces. In the last years of his life, Hawking was still working on this problem. His final scientific paper, published just days after his death in 2018, was a collaboration with Malcolm Perry and Andrew Strominger, and it proposed what they called soft hair on black holes, a mechanism by which information might be stored on the event horizon itself in subtle quantum effects that nobody had previously accounted for. It was not a complete solution. It was a direction, a door cracked open. He did not live to walk through it. Stephen Hawking died on March 14th, 2018. He was 76 years old. He had been given 2 years to live when he was 21, which means he spent approximately 55 years on borrowed time, using every one of those borrowed years to do work that the universe is still catching up with. And I want to be precise about that number because it matters. 55 years. If he had died on the doctor's original schedule, we would have none of it. Not the singularity theorems, not Hawking radiation, not the information paradox, not the bet with Kip Thorne, not the soft hair paper, nothing. Everything we know about the quantum mechanics of black holes, the entire branch of physics that has consumed some of the most brilliant people alive for 5 decades, traces back to a man who was not supposed to be there. Here's the part I think gets lost in the inspirational version of this story. People talk about Hawking as a triumph of the human spirit over physical limitation, and that is true, but it misses something darker and more important, because the body does not disappear when you talk about the spirit overcoming it. The body was there every single day. By the late 1970s, Hawking had lost virtually all motor function. He could no longer write. He could no longer feed himself. He communicated through a speech synthesizer, first operated by a clicker he could hold in his hand, and later, as even that capacity faded, through a cheek muscle that could detect the movement of his glasses. One muscle in his cheek. That was the entire physical interface between Stephen Hawking and the rest of the world in the last decade of his life. And through that one muscle, he was arguing with the smartest people on Earth about the nature of information in the universe. I do not say this to perform awe. I say it because it changes the calculus of what he could actually do. A theoretical physicist's most important tool is extended calculation, working through long chains of mathematical reasoning, checking steps, revising, seeing where the logic leads. Hawking could not do this in the traditional sense for most of his career. What he developed instead was something his colleagues described as almost eerie, He could hold entire mathematical structures in his head and manipulate them spatially, geometrically, without writing them down. He could see the shape of an argument, the way a musician hears a chord progression as a whole, not as individual notes in sequence. This is not a compensation. This is a different kind of thinking. And it produced a different kind of result. Hawking's ideas tended to be conceptually vivid, geometrically intuitive, and often arrived at conclusions that the formal mathematics took years to either confirm or reject. Sometimes he was right, sometimes he was wrong, but he was almost never boring. And the problems he pointed at were almost always real. The one bet he lost more publicly than any other was a bet with Kip Thorne again. This time, also involving a physicist named Gordon Unruh, about whether a specific kind of X-ray source called Cygnus X1 was actually a black hole. Hawking bet it was not, as a kind of insurance policy, he said, because if black holes did not exist, at least he would win the bet. Cygnus X1 was confirmed to be a black hole. Hawking lost and sent Thorne a subscription to a certain adult magazine as the agreed prize, which Thorne's wife apparently did not appreciate. Physics bets are a whole genre. Now, here is what I think is the most underrated thing about Hawking. And this is the piece that lands differently when you have the full picture in front of you. He made physics accessible in a way that nobody had before him. A Brief History of Time, published in 1988, spent 237 weeks on the Sunday Times bestseller list, 4.5 years. It sold more than 10 million copies in the first 20 years after publication. It has been translated into 40 languages. For context, Carl Sagan's Cosmos, which was already considered a landmark piece of science communication, sold around 5 million copies over a similar period. Hawking doubled that. But here is the piece that always gets buried in the sales figures. A Brief History of Time is hard. It is not a pop science book in the modern sense, where the author smooths every edge until nothing is difficult. It asks real questions. It describes real physics. And millions of people who had never thought about black holes or the Big Bang or the nature of time picked it up and worked through it because the voice in it was so direct, so unintimidated by the material, so honest about what we do and do not know. That voice did not come from nowhere. It came from a man who had spent 30 years living inside these questions, not as intellectual puzzles, but as the organizing structure of his entire existence. When you have the kind of diagnosis Hawking had, you are not exactly casual about questions concerning time and how it ends. The information paradox matters, and I want to come back to this because it is the actual philosophical core of everything Hawking touched, because it is not really a question about black holes. It is a question about whether the universe is fundamentally knowable. If information can be destroyed, then the past is not fully recoverable in principle. Not because our instruments are too weak, but because the universe itself has deleted its own records. The universe forgets. And if the universe can forget, then certain questions about what happened before, what caused what, where things came from, have no answer, not because we haven't found it yet, but because the answer is gone. That is a deeply uncomfortable idea if you are a physicist who believes the laws of physics are time-symmetric and complete. It is also, depending on your metaphysical disposition, a strangely liberating one. Not everything that is lost leaves a trace. Some things are just gone. Hawking sat with that possibility for decades. He argued for it, walked it back, proposed partial solutions, and died still working on it. And what is remarkable is not that he did not solve it. What is remarkable is that he found it in the first place. The information paradox was invisible to physics until Hawking radiation made it visible. He did not just discover something about black holes. He discovered a new way that the foundations of physics could be broken. The most dangerous discoveries are not the ones that give you answers. They are the ones that show you new kinds of questions. Now we are almost at the close, but there is one more piece, and it is the one I think matters most. Hawking radiation, as I mentioned, has never been directly observed. Not once. No telescope, no particle detector, no gravitational wave instrument has ever seen it. For a black hole with the mass of a star, which is the smallest kind of stellar black hole we know about the radiation it emits, is so cold, so faint, it is approximately 100 millionth of a billionth of a billionth of a degree above absolute zero. We have no instrument remotely capable of detecting that. We will not have one in your lifetime. We may never have one. Which means the single most celebrated result in theoretical physics in the second half of the 20th century, the result that almost every physicist alive believes to be correct, the result that connects quantum mechanics to gravity in a way nothing else does, the result that generated the information paradox and the firewall paradox, and Hawking's final paper, that result, exists entirely in the mathematics. We believe it because the math is right, because independent approaches confirm it, because it fits into the larger structure of what we know about quantum fields and curved spacetime. But we have never seen it, not even a shadow of it. This is the nature of theoretical physics at its edge. You are doing experiments that reality cannot currently perform for you. You are reasoning about conditions that no laboratory on Earth can reproduce, processes that unfold over timescales longer than the current age of the universe. And you publish anyway, because the math is true, even when the observation is impossible. Stephen Hawking spent his entire career here, at this edge, doing physics that the universe would not confirm for centuries or millennia, if ever. And he did not find this frustrating. He found it exhilarating. The fact that a human mind could reach further than any instrument, could derive true things about the universe, that the universe would not bother to demonstrate for longer than civilization has existed. He thought that was the most extraordinary thing about us. He said once that, however bad life may seem, there's always something you can do and succeed at. He said that while life continues, there is hope. He was talking about his disease, but he was also talking about physics. He was also, I think, talking about the same thing. When I go back to that night in January of 1974, Hawking in the dark, getting into bed, holding the shape of Hawking radiation in his head because he had nowhere to write it down, I keep returning to what it cost to get to that moment. Not the disease, not the limitations. The 50 years of borrowed time. The fact that the doctors had already written off the next 50 years of his life before he had a chance to use them. Every equation he ever derived after 1963 was, in a very real sense, a bet against the expected outcome. A personal demonstration that the universe had not yet closed the door, that there was still one more thing to find. Roger Penrose, who started this whole journey by showing Hawking that singularities were real, who gave the dying graduate student a reason to finish his PhD, went on to win the Nobel Prize in 2020 for work on black holes. He was 89 years old when he accepted it. Physics has a long memory. The bet between Hawking and Kip Thorne about the information paradox was eventually conceded by Hawking, but never truly settled. Thorne is still not fully satisfied. Preskill has his encyclopedia. The question is still open. And somewhere in the mathematics of what happens when a black hole finally, after an unimaginable span of time, evaporates completely, the answer is waiting, patient, not going anywhere, which is more than you can say for the black hole. Stephen Hawking was not the first person to study black holes, and he will not be the last. But he is the person who showed us that they are not simply the end of things. They are a question, the most fundamental question physics has ever asked. Whether the universe truly remembers everything that has ever happened, or whether some things are simply irretrievably gone. He did not solve that question. He lived it. And the night he lay in the dark in January of 1974, having just discovered that the most permanent seeming objects in the universe are slowly dying, unable to write it down, unable to tell anyone, holding the universe's secret in a mind that was one of the last things his body hadn't yet taken from him, that was not the end of the story. That was the beginning of the question.